Throughout this training, or at any time you need support, there are many ways to contact us. You can follow us on all major social media platforms or email us directly via our website, or you can click the Cancel Connect icon shown at the bottom of this slide on our website to book a consultation with one of our experts.
Okay, so we've gone into more detail with the 6 charts that we introduced in the measure phase. We introduced those 6 charts in measure because they are great tools to show your baseline measures as well as strong data analysis tools. Now we are introducing 2 more data analysis tools that are commonly used in the analyze phase to test your hypotheses.
The first is the scatter plot. The scatter plot shows the relationship or correlation between a continuous or numerical y and a continuous or numerical x. The second tool is the chi-square test, and this test requires a discrete y and a discrete x to determine whether the difference that we're seeing is significant. Let's start with the scatter plot. In this chart, we're comparing 2 variables, a y and an x, and they both must be numerical or continuous. In our sample data here, our y is craft beer sales, and the variable that we're studying is temperature. The hypothesis is that as temperature increases, so do beer sales. So the data is put in columns and we simply insert a scatter plot, also called an XY scatter, and this chart is returned.
The scatter plot uses paired data, meaning that we have collected 2 pieces of information for each dot on the chart. Each data point is positioned according to both the y and the x values. And it's the pattern of the data that tells us about the relationship of the x to the y.
The first pattern that we'll look at is the pattern that we saw in our beer example. This is called a positive correlation. As x increases, so does y. A few more examples of positive correlation might be hours studied for an exam and the exam grade, or calories consumed per day and weight.
The next pattern that we see is a negative correlation. The negative correlation shows that as x increases, y decreases. We might see this pattern if we studied the number of hours exercised per day and add weight. The third example is called a curvilinear relationship. This means that as x increases, y goes up to a point and will then start to decrease. A good example of this might be productivity and overtime. As the overtime hours increase, productivity goes up to a point and then it starts to diminish as people start to burn out or get tired.
The last pattern is no correlation at all. This pattern shows when there's no demonstrated relationship between the x and the y. So as x increases, so what? But it's not only the shape of the patterns, but also the tightness of the dots. So the closer the data points are together, the tighter or stronger the relationship. In other words, if the data points are close together, you have a really strong x variable or causal factor there. And if the data points are pretty wide apart or loose, while there may be a relationship, there are other significant causal factors affecting the results as well.
Now, fortunately, we don't have to rely on our own judgment of tight or loose with the scatter plot. There's a couple of numbers that will tell you the type and strength of the relationship. And those numbers are the correlation coefficients, also known as R and R squared. The correlation coefficients are numbers that indicate the strength of the correlation between 2 factors. R is the strength of the direction of the relationship and always falls between -1 and 1, and it can be calculated in Excel with a simple formula. 1 is equal to a perfect positive correlation and -1 is a perfect negative correlation. The value R tells you if there is a positive or negative relationship between the 2 factors. Any positive or negative value for R that is less than -0.65 or greater than 0.65 could be considered to have a meaningful degree of correlation.
Just a note, one drawback of the correlation coefficient is that it does not provide a meaningful number for curvilinear relationships. For those, we have to do a little bit something different and plot the data. That's black belt territory. If we look at our beer sales data, we can use this simple Excel formula to calculate R, and we get a value of 0.96. That's a positive number, and it's really close to a perfect positive correlation of 1. That means that an increase in the variable of temperature is strongly correlated to an increase in beer sales. To find out how much, we just square R. So 0.96 times 0.96 is R squared, and it comes out to 93%. So what do we do with that number? That means that 93% of the variation in beer sales can be linked to the temperature. R squared is the percentage of variation that can be attributed to the X variable.
And just like with the other charts, the 1-point lesson for the scatter plot shows you how to create the chart in Excel, and also how to interpret the chart. Once you start working with these charts correctly, you'll notice how few people understand how to actually use them. And that's a great benefit of being a certified green belt. You can have a big influence on how your whole organization understands data.
Chi-square test is a tool to understand statistical significance. It provides more conclusive evidence to either support or refute a suspected hypothesis. Chi-square is one of many hypothesis tests, and it analyzes differences in proportions for one or more sets of data. So because we're using proportions, it requires that both the y and the x are discrete.
There are two types of chi-square tests: the goodness of fit and the test for independence. The goodness of fit test compares the actual observed values to a standard or expected values to see if there's a difference in the two proportions. So we might use the coin flip example as a way to test the goodness of fit. If we are flipping a fair coin, we would calculate the expected values roughly 50-50 for heads and tails, and then compare those expected values to the results from our actual flip results to see if the proportions are statistically the same. We can also use the goodness of fit test to compare our observed results to a standard or a world-class result. Anytime we are comparing results to an expected result, we would use the goodness of fit.
Now the test for independence is the same concept, but instead of comparing to expected or standard values, it compares different groups to each other. So we might be testing the proportion of defects from 5 different locations to see if the differences that we see are significant. The test for independence is more common for a process improvement project. The results from one group to another will rarely be exactly the same. So the test for independence is looking at the different groups and determining if the differences we're seeing are random or significant.
In this example, we are studying whether people like the new check-in app, and our survey data doesn't really show a clear difference in the proportion of like or not like between men and women. We have a discrete Y, which is like or doesn't like the app, and a discrete X, men and women. This is a great candidate for a chi-square test. We have no standard or expected values here, so this is a test of independence, to see if the results from the women are independent from the men's results. Just looking at the numbers, it looks like there may be a difference, but we can't be sure that it's statistically significant. We want to see if there's a significant association between gender and the new app preference.
There are many online calculators for chi-square, and in a process improvement project, you'll most often be using the test for independence to see if the group that you're studying is different from the other groups. Here's an example of an online calculator. It just requires you to enter the table information and the calculation gets done for you. You'll see that you'll get a p-value returned to you, which will let you know if the differences you're seeing are significant. And in our study of the new app preferences, we see that the p-value is 0.03, which is less than 0.05. The null hypothesis would have been that there's no difference in preference between men and women, but the p is low, the hoe must go. Statistically, gender is a factor in the app preference. In this example, we're studying whether we have a fair coin. We have a discrete y, that's the number of heads and the number of tails, and the discrete x, that's the expected and the observed. This is a great candidate for a chi-square test. We have an expected value here, so we'll use a goodness of fit test to see if the results fit the expected results. Just looking at the numbers, it looks like there might be a difference, but we can't be sure that it's statistically significant. We want to see if our numbers are off enough to be considered meaningful.
Again, let's use an online calculator. We first enter the information from our table, which has the expected and observed values. The online calculator is asking for a significance level, which defaults to the standard value of 0.05. Then just press the button to calculate chi-square. Very simple.
In our example, we see that the p-value is 0.0027. The result is lower than 0.05, so we do have a significant difference. Our coin flip results are significantly different than what we would have expected if we were dealing with a fair coin.
So we've covered the two types of chi-square tests. And as we learned, it can be a great tool when you need to distinguish differences, especially when it's hard to see with the naked eye. Here's a quick one-page lesson on the chi-square test. It has been our sincere pleasure being with you through this part of the training, and we thank you for your dedication to creating a better workplace and an environment that you can truly enjoy.